ready, 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 ready. When I plan my attack, I doubt that you're ready. You're ready. I doubt that you're ready.
And today it is my pleasure to talk to you about machine learning powered metabolomic network analysis. So I'm kind of going to start off by discussing the kind of predictive analysis and statistical analysis that we're currently doing metabolomics, and the things that are done and the methods used to kind of connect this data with the biochemical context. Then I'm going to kind of showcase some tools I've been working on to kind of help integrate the various information and include network analysis and machine learning all together. And then finally, I'm going to end with the kind of a little bit thinking to the future. What might metabolomic analysis look like in this kind of age of big data and deep learning? So what does predictive modeling within a biochemical context look like in metabolomics right now? So oftentimes we might be doing studies where we're very interested in biomarker discovery. And so we might have a cohort of sick and healthy patients, and we measure their metabolites. And then what we'd like to do is identify differentially expressed species or relationships that can best discriminate between our sick and healthy population. And we'd like to identify a few markers which can help us identify disease onset or prognosis or disease efficacy monitoring, things of that nature. So other things we might be doing are conducting metabolomic studies for personalized medicine pursuits. And so what we might do is we might have a very large kind of population cohort where we study the interaction between individual circulating metabolite levels and how they respond to various drugs. So for example, in cancer treatments, or even in treatment of metabolic syndrome like lipids. And so what we'd like to do is essentially develop a model that links what your metabolome looks like to how you will respond to various drugs. And then when a patient comes to us, we'd like to measure their metabolites and then predict what is the best kind of combination of drugs or drugs they should be using, or even more importantly, which drugs are going to have no benefit to them or could even be detrimental to them. And so doing this kind of work, working in metabolomics, we're really having to do all sorts of complex data integration, because metabolomics, it combines a lot of actually complex biochemical domains under its umbrella, but also we have complicated studies. We might have multi-year studies or complicated time courses. And so one challenge is, how can we get at the important biomarkers or even systems markers, within this context of these complicated experimental designs? And so what I'd like to talk to you about today is essentially how we can use network analysis and how we can combine that with machine learning and all of our statistical and functional tools to begin moving forward, away from just single biomarkers of this disease state and towards kind of systems of changes. And so I think this is an important designation, because where before we might have one good biomarker, somebody identified it, and then later it might fall apart and no longer works, and we're kind of wondering why. Was the study flawed? Was the population not applicable? And so what I would argue is that it's really a system of changes, that no change in metabolism is kind of an island. There's always a lot of other things going around, and your biomarkers are interacting with other systems. And so it's going to be to our benefit to analyze and interpret our data kind of on a systems holistic level. And it's okay to see where the biomarkers are, but we should also see their neighborhood and their surroundings at the same time. And so a little bit about the present and the future of metabolomics. So here's a quote from a recent Science article. So I will preface that these gentlemen are quite biased toward the genomics area, but here's what they say. They say the impact of metabolomics on systems biology is still in its infancy. Few people have a solid understanding across all the omics, including lipidomics and epigenetics. And I think that's very true, and so what he's hinting at is that we're kind of a little bit siloed in our work. So in metabolomics, it's highly specialized. It's very difficult. The kind of analyses we do don't really translate across the domains. And so ideally where we'd like to get to is kind of following a second quote is that there's a need for generalized data analysis methods capable of efficiently integrating across and within omic domains. So we need to think about what kind of tools can we use that can generalize, that we can use to combine maybe our genomic, our lipidomic, glycomic, all of this information together. And so even just within metabolomics, I mean, when people say just metabolomics, I mean, it's not just metabolomics. To kind of do this large metabolomic studies and try to measure as many metabolites as we can to understand complex physiological systems, we're using many subsets of omics, like lipidomics, maybe shotgun central metabolism metabolomics, maybe signaling lipids. We're using even a different instrument. So even doing this, we're already using many different instruments, many different analytical methods, different processing methods, and then we need to think about how are we going to integrate all of this data together? How are we going to make sure that the analytical trends within one instrument don't kind of swap out the biological signal or some small effect size in another instrument? And so to do this, we really need to think about kind of the materials of connected biological data analysis and visualization. And really, it all starts at the experimental design. And this is a very complicated topic. I'm not really going into it, but you have to design your experiment correctly and also build in the appropriate measures to allow you to do probably one of the most important steps is the quality assessment. You need to make sure that the trends you're observing in your data are not due to some kind of analytical artifacts, that they're not due to how you process your sick patients in one batch and all your healthy patients in another batch, or they're not due to the fact that you use different instruments, you know, across 2 years, or your column was dying and your signal intensity was going down. So you need to kind of build in these controls to avoid this. So once your data is of quality and you've assessed that, now you're ready to do statistical and multivariate analyses. And so this is where you're going to use kind of measures of your experimental design to maybe identify the top discriminating metabolites between sick and healthy patients. You might then overview the multivariate trends just to see what other kind of insights you might gain on a supervised or unsupervised methods. And now that you have this information, typically the next step is to then use some kind of functional analysis or maybe a pathway analysis where you take the things which are important for discriminating your sick and healthy cohorts and you project them into this biochemical context of a pathway. And so pathways have a lot of good properties, but I would say you shouldn't stop there. You should go on and do some network and predictive modeling with your data. And so what I'm going to talk to you about more today is essentially how we can build networks. We can incorporate the same information we get out of the pathway, but we can incorporate even more information. And we can layer our statistical analysis with the multivariate machine learning-based predictive modeling to give us another kind of orthogonal layer of robustness to our insights, and all the while kind of visualize and analyze all of our information together holistically as a system. So I've been spending a lot of time kind of thinking about how you can design software that allows you to kind of integrate these various layers of analysis. So moving from data pre-processing to a statistical analysis, multivariate like clustering or PCA, incorporating functional tools like pathway modeling, and finally get that all together within a network. And not only move linearly forward through your analysis, but also be able to, when you gain insight in one step, to be able to go back in time and go to a previous analysis, update your assertions there, and then have all of that nicely integrated in the form of a report that you can kind of track. It can be very reproducible to what you're doing. And so I've been working on a software called DAVE, and stands for Data Analysis Visualization Engine. And so you can do things like conduct a statistical analysis. And so probably the simplest representation of statistical analyses would be like a two-class comparison. And I would argue that pretty much any complicated analysis can be reduced simply, and often is, to a two-class or a pairwise comparison. So here's an example where we've compared the circulating metabolite levels between diabetics and non-diabetics. This is a univariate test that we do for each variable one at a time, but now we're showing all of these results together in the form of this volcano plot. And so what you see is on the x-axis, we have the fold change difference in the circulating metabolite levels between diabetics and non-diabetics. And on the y-axis, we have the significance or the p-value of that test. And so the things in yellow essentially don't meet our cutoff criteria. And so the things which are in blue and which are labeled, these are the things which we are now focusing, which are significantly altered in diabetics compared to non-diabetics, and also they're of a large magnitude. So we would say it has a large effect size. And so looking at this plot, you know, your eyes might be drawn to some of these species over here, like 3,6-anhydrogalactose. So it's very significant. It has a low p-value, a large magnitude of change, and it's increased in diabetics. Now, on the other side, we're also drawn to this one species here, 1,5-anhydroglutatol. So it's also significantly changed. It's a large magnitude, and it's also the only species that's decreased in diabetics. So that's interesting. So this is some insight. And so immediately for me, like looking at this visualization, I have some questions that come up. For example, for all of the species that are increased, are they actually related to each other? Is 3,6-anhydrogalactose related to maybe fructose? Are they part of the same pathway? Are they correlated? The other question I have is, well, if I'm going to pick two of my top biomarkers just based on this, 3,6-anhydro and 1,5-anhydroglutatol, I want to know, are they related? Are they correlated? Are they structurally related? Why? Is there any biological reason that both of these are good biomarkers for type 2 diabetes? So starting with a statistical analysis, next useful thing to do is multivariate. And so essentially, let's look at the data trends giving all of our samples or all of our variables. And so this is actually also an important distinction, is that we can look at our data matrix as it is, as rows or columns, or we can calculate correlations between our samples or our variables. And so a very powerful and often used technique is clustering. And so here's an example of a hierarchical clustering. And so essentially, clustering is comprised of two parts. So part one is distance. So essentially, you define similarity or dissimilarity between all of your variables or all of your samples. So you embed it in some kind of a distance-based space. Once you have this distance, then you use an agglomeration or a linkage methods to essentially build up relationship, pairwise relationships from the first two most similar to the next most similar to them, and you kind of build this up. And oftentimes how you visualize this is in the form of a dendrogram. So here's an example of a dendrogram. And the way we interpret these is essentially the lower down two species are linked, the more similar they are. And so here is an example of a hierarchical cluster output where the data is organized using hierarchical clustering. You see the dendrogram on top, but in the middle, we're also showing you the correlations between all of the samples. And so the other important thing is that we want to layer on top our metadata to see, does our metadata, which is not used to cluster this, does it explain the kind of cluster patterns? And so here, this top row is showing who is a diabetic and who is not diabetic. And so looking at this, we might see that here we have this pretty nicely defined kind of part of the cluster, and they're mostly diabetics in here, but there are some misclassified samples, so there are some non-diabetics. Similarly, we look over here, there's a large cluster of non-diabetics, and so we have some diabetics in here as well. So essentially, these are individuals whose profiles look like the other class. So some questions we might ask, well, is this a mix-up? Hopefully not. What other information can we layer on this? Could it be their age? Could it be their gender? Right? So we can add more to see what explains that. The other powerful thing that hierarchical clustering gives us is essentially we can empirically segment our data. So this lower panel is showing us the hierarchical clusters. So if we were to break our data into three groups, this is what it would look like. So again, we see that this is kind of a nice subset. It's together. But what's even more interesting is that now we've segmented our non-diabetics into two groups. So here's this one group that's all non-diabetics. So this is a very strong signal of what non-diabetics looks like in your data. We look at the correlation matrix, we see that yes, they're highly correlated, and even within here, there's another subset of these are the most similar to each other, and very strong non-diabetic signal. So we can include that kind of information, like for example, maybe we're looking at drug response. This could be a stratification of who is and is not responding. You know, within our knowledge of metadata patients, we can get further level of this kind of segmentation. So now that we've done some hierarchical clustering, Other very useful multivariate techniques include methods for projection. So these are dimensional reduction techniques like PCA or principal component analysis, MDS or multidimensional scaling, even things like t-SNE or t-stochastic neighborhood embedding. And so what these methods allow us to do is where before in the hierarchical clustering we organized our data really in one dimension. But now we can essentially look at the n-dimensional relationships of every variable and every other variable. And so imagine this n-dimensional hypercloud, and then we can find the different bulges in that cloud and then project that, or look at the shadow and project this shadow on a two-dimensional plane that then we can analyze. And so here's an example of a principal component analysis sample scores for the same diabetic and non-diabetic population. And so in this PCA, we interpret similarity in samples is now defined by proximity in this space. And so here again, we have some metadata. So we're showing using this Holtling squared t-squared ellipsis to show us kind of the bivariate distribution of our diabetic cohort and our non-diabetic cohort in this space. And now what we've done is we've added some more metadata. So now we label these samples as are they old or are they young? And so now it's interesting to see that some of the previously labeled samples previously misclassified non-diabetics who look very diabetic. Now we see that they're also old. They're also older, and it's kind of well known in literature that there is definitely an interaction between age and your glucose control. So having this kind of insight, one thing we might say is that, well, we need to update our statistical analysis strategy to include this covariate of age. So we need to look at how change the metabolites are interacting with both type 2 diabetes and age, and then type 2 diabetes age interaction all together. So now that we've done that, the new addition that I would advise kind of to incorporate into your analysis, essentially do the same kind of work, but now do it within a predictive modeling kind of machine learning framework. So develop a multivariate classification model to best predict who is diabetic and who's not diabetic. And so to do this, you're going to have a lot of options of models to use. And so some things you're going to want to ask yourself are, well, which one is appropriate, to my data? So it's important to note that different methods will handle different missing values in different ways. Like, for example, many will impute the missing values in different ways, or they'll completely exclude them. Some methods can actually make the models without excluding anything and just keep them as missing values. The other thing to consider is, how does the algorithm handle numeric and discrete variables? Can it handle it simultaneously? For example, maybe I observe that age is an important covariate. And so in a machine learning framework, I would include age as a variable. But this is a variable that's discrete, so it's labeled. It's old and young. And so methods like orthogonal partial least squares, or OPLS or PLS, well, those couldn't really handle this kind of a discrete variable, so it would just convert it to numeric. So you kind of miss the kind of level ordination that you would get otherwise. So maybe you would look at other techniques like random forests that very nicely would handle both discrete and numeric parameters. So the other thing you need to consider is multicollinearity. So this is essentially when you're modeling with a lot of variables which are highly correlated, which is the reality of metabolomic data. You need to be very careful, because when many things are related, it's difficult for the model to determine the impact of any one thing among many correlated species. So for example, if you were to make like a linear model with enough parameters and they're highly related, you'd get very unstable measures of the coefficients and the error. And so you essentially wouldn't really know which one is contributing more or less. You would have some fit, but you couldn't really interpret it. The other important thing to consider is fitting properties. I think most models used in metabolomics are completely linear, but in reality, if you actually look at the trends, you might notice that, well, most of the relationships are actually nonlinear or somewhat nonlinear. And so, for example, methods like random forest, that's a great method to capture nonlinear trends as well as linear. And so that's quite a bit of options. So how can you actually choose if you're not really familiar with the method, so you don't have kind of insight or domain knowledge in the area? Well, what you can do is kind of use the principles of kind of this machine learning framework or model validation, and use this idea of training and testing to actually identify the best model for your data. And so the way this workflow goes is essentially you take your full data set and you split it. So you might take 2/3 of the data, and this is your training set. Now the other 1/3, this is your holdout set. You're not going to touch it. You're not going to look at it. You're going to use it at the very end to kind of check yourself. How good are you really doing? So what you can do is you can take your training data, and you can try a variety of different models. Try to optimize them in different ways and identify what kind of tuning parameters, what kind of accuracy metrics you can be using to kind of optimize your models. Is it sensitivity, specificity, things like that? You can also carry out feature selection, which is actually a very powerful thing. So essentially feature selection is we can use a machine learning model to iteratively pick different subsets of our variables and then fit models to those subsets. And then what we look at is we look at the error in our classification or prediction, and we, after trying many subsets, we identify the subset that gives us the lowest error. Now this is very important and powerful. So essentially now we have a model which has typically far fewer features, and they give us the best prediction. So we get better prediction with these fewer species than with all of our data. So this is also would be analogous to a statistical test where, say you identified something is significant, so you have this subset of your important things that you're looking at. Now you have another layer. You have all of your things which are included in your optimal model. So this is kind of an orthogonal measure of significance. And the other powerful thing that you get is from your model is that you get the predictive performance. You have a pretty good estimate, hopefully, of how well it's going to do on future data. And so this gives you a lot of confidence for its generalizability. The other powerful thing that you get from predictive models are feature weights and ranks. Now, not all models will give you this, but the models which are nicely applicable to metabolomics, like OPLS or a random forest, you can get the weights. And so essentially what this allows you to do is now we can rank all of our variables in order of their increasing contribution to the model's performance. Now this is very powerful because where before, if we did just statistical tests, we just have something is significant or it's not significant. Something cannot be more significant. We might want to rank by fold change, but that might not be a good rank. But now we can actually rank by each variable's contribution to a predictive model, and that's going to give us a far more robust rank. So in working on Dave, I've been thinking a lot about, how can we make this kind of machine learning experience, user-friendly to, folks that haven't really tried this before or aren't as familiar with the various techniques. And so what I've been building is a user experience where you can choose from over 200 different model types. You can come in and use some automated parameter tuning workflows where essentially we'll just fit lots of models, we'll set up a tuning grid, and we'll identify the parameters that will minimize your error. Or if you know what you're doing, or if you read up a little bit about it, you can also do things manually. You can specify all your parameters. And so you have very fine control of what you're optimizing. Maybe sometimes you want to be very sensitive, sometimes you want to be very specific. So you can tweak all these knobs, and all the while really control your cross-validation, and in the end use your test set to really validate that you didn't overfit, that you've made a good model, and also include all sorts of feature selection algorithms to help you kind of get at the key model optimization metrics. So, okay, so now that we've done that, we've conducted our statistical analysis, we've looked at the multivariate trends, we've identified our optimal model parameters to kind of optimize our prediction of who's sick and healthy. Now we're ready to conduct a pathway analysis. So this is really kind of our first opportunity to now interpret this data, or all of these insights, within a biochemical context. And so a pathway is an expert definition of a biochemical module. So here's an example of the pentose phosphate pathway. And so what I've done here is I've mapped the fold change difference between diabetics and non-diabetics onto the nodes, which represent the metabolites, and the squares in between them would represent proteins or genes. And so we can also do a similar mapping if we have those species. And so what this allows me to do is now, well, I can visualize these important changes in this biochemical context. I could map my data, different metrics. So maybe I want to map the machine learning model rank on top of this. Maybe I don't want fold change. Maybe I want to map the p-value. Other things, analyses I could do would be something like enrichment. So I can ask the question, of the things which are important or significantly altered, is there some overrepresentation above random chance within a specific pathway? And so here we'd be using some kind of domain knowledge. So this is a representation of KEGG. So we'd use the KEGG database to determine this. Other interesting analyses that we can do is essentially include this idea of topology, where essentially changes in species which have a lot of children or a lot of metabolites produced from one metabolite, we would say those are more important from, say, a metabolite that's kind of a dead end at the end of a pathway. So in this example, for example, if I was comparing changes in deribulose 5-phosphate and D-ribose, I would say changes in deribulose are more important because they have more dependence. So they can impact a larger swath of biochemistry than D-ribose. Now, networks are very nice and very powerful tools, but kind of one thing that's missing is that, one, they're kind of this expert definition of what a pathway is. And so one thing you might have missed in the previous network is, you know, D-ribose might have many, many more connections to many other species I might be interested in, but they're just not part of that pathway. And so for me to kind of see all these connections, I would have to look at many pathways and kind of keep them in my mind. So that's one option. Or another option is what I can do is I can take all of those biochemical connections in those pathways and I can just calculate a network. So essentially, so this is an example of doing just that, where this is a metabolic network combining over 1,200 different metabolites. And so now what we've done is we've taken those connections we saw in the pathway and now they're represented as these hashed red lines. So these are biochemical transformations. Now, the other important thing we've done is that we're also linking metabolites using other information, other relationships. In this case, the gray edges are actually structural similarity. So structural similarity turns out to be a very powerful method of kind of grouping your metabolites. And so we know that there is a structure-activity relationship. And so using these edges, we can kind of tighten our connections in species where there's very little to no kind of biochemical domain knowledge. So for example, lipids, you know, it's very kind of hard to really determine the biochemistry of how our lipids are interconverting, shortening, saturating, desaturating, but we can get a good grip on just looking at their functional groups. And so how is this done? So I'm going to spend a little moment to kind of give you an idea of the data structures that we're using to build up these networks. So here's an example. So let's encode this biochemical reaction. So here we have a reaction from KEGG. This is to the conversion of lactate to pyruvate. So the first important thing we do is we translate the synonym, the name, to a unique database identifier. So this is an important step that's not really often considered, but many of us might start with different names or different synonyms for the same exact thing. And so this concept of database ID translation is actually not very easy. And so this is very important. So we encode it in a unique identifier. So now any name mapping to that will capture it as a right molecule. So now that we have kind of this equation for this reaction, how do we put it into a network? And probably the simplest and most useful data structure in my opinion for networks is this idea of a node list and an edge list. And so all a node list is, it's really a list of your metabolites. And so in a network, we call them nodes, so we can call them a vertex. And so it has an identifier. This is its unique key that's going to map all across the network. It might have some metadata, like it has a name. And so here are our nodes, our pyruvic acid and lactic acid nodes. And the edge, the connection, we call it an edge, that's encoded in our edge list. And this is simply, minimally, just a 2-column list of from, to, source, target. And then so in this case, it's actually, this is a reversible reaction, so it has no direction. So we would call this an undirected network. So, but we need not stop at the KEGG connection. Now, you know, these biochemical connections are very powerful, but what we can do is we can add other information, like molecular fingerprints. For example, for each molecule, we could look at the functional groups and we can count how many functional groups they have in common and calculate distances between them. And then we can use that to create a network connection based on some threshold. The other interesting connection is mass spectra. And so essentially, what we can do is we can compare the mass spectra and actually calculate mass spectral similarity. And what this allows us to do is essentially we can take our unknowns, where all we have is this mass spectra, and we can calculate and identify which known their spectra looks most similar to. And so now this is very powerful because now we can connect our unknowns to our knowns in our network. Now the other very powerful connection is the empirical, or the correlation or partial correlation connection. And so these are the relationships in your data which are specifically dependent on your experimental design, on your experiment. And what's nice with these is that they're not unique to the metabolomics. You can include genomic or proteomic or any other kind of data, and you can pretty easily calculate the connections. And so what you would get is, a group of metabolites went up, and also some gene expression also went up at the same time. So they were related or correlated to each other. Now that's the step of generating your network, but the next thing you want to do is you want to be able to map and integrate all of the statistical and functional analysis and tools on top of that network. And so this I term network mapping. And so you can think of your network as a big coloring book. So this is your context. These are all of the possible relationships. This is where you need to stay kind of within the lines. Now your mappings, the things you calculated, is something significant? What is the p-value? What is the rank in the machine learning model? What pathway does it come from? These are all of your crayons. And so the process of network mapping is to then use this information to color your network, or essentially alter your node or your vertex attributes or your edge attributes to essentially encode that information in a manner that you can visually kind of determine, and it communicates to you, and you can analyze it, and you can also test hypotheses on this network. And so kind of one of my goals with Dave, and really why I designed it, is essentially this is the step that I'm really interested in. And I personally found it laborious, and I'd have to use many different softwares to kind of get here. And so really my goal is to get a single software that can kind of do it all, and then really focus on this network mapping aspect at the end. And so it's useful to kind of think about what data structures are we using to do network mapping. And as it turns out, the node and edge lists are actually great structures to hold both kind of connection information and metadata. And so, for example, what we can do is we can take our original node list. It had an identifier and it had a name. And now in that same node list, we can store all sorts of metadata that we build up during our analysis. So now a metabolite has an ID, it has a name, it has a p-value for some statistical test. It was up-regulated in our comparison. It might have a specific rank in a machine learning model. And what we can do is then all of these features are now available. We can now pipe them through our network attributes to essentially alter how our network looks. And so we can ask the questions like, in which biochemical domain are there most of the significant changes are happening? Or where are things going up versus going down in type 2 diabetes? Are they correlated, or is it a biochemical connection? And we can do this in real time, right? It's kind of like the ideal case is that you have this structure, and then the user, you have these emergent kind of use cases where the user maps different things and discover different things about their data and kind of iterates over it. And so the other nice property of the edge list is that it's completely additive. So we can take a biochemical network and we can add it to a correlation network or add it to a structural similarity. And so we can make all sorts of very unique combinations of networks very easily. And so that's a little bit about kind of the present, what I think of metabolomics. And so now a little bit about the future. So here is a quote from the same article where they say, metabolomics can't really function on its own without the genome sequence. Now, these individuals might be correct, but as I mentioned, they're also highly biased. So they're not really doing metabolomics primarily. So I would flip this statement. And so one thing that's often forgotten or not often kind of considered is that we're interested in the phenotype. Who is sick and who is healthy? That is their phenotype. And we know that the phenotype is the interaction between our genotype and the environment. And in my opinion, there is no better way of measuring the environment than doing metabolomics. Metabolomics can capture your environment, what environmental toxicants you're exposed to, what did you eat in your diet, pollution, all of these kind of integrated things integrated into your body, and we can do it in real time. So what I would do is I would flip this, and I would say, that in the future, we kind of see this explosion of this personalized genomics and looking for SNPs and, essentially risk for diseases and things like that. I would say that is going to be far more powerful if this genome sequence information is done in combination with metabolomics, which gives you the real-time feed out, essentially, of how these risks and genes are interacting with your lifestyle, with what you're eating, what you're exposed to. So it's not a matter of or, genomics or metabolomics. I think it's going to be always and. It's going to be different omics and metabolomics. And so why is this so useful? For what kind of power are we gaining? So just like I previously mentioned as I started out, that we'd like to move away from the single biomarkers and move into kind of systems of changes. The same is true for looking at the various kind of omics levels of hierarchy. So what we'd like to do is, in those cases where we saw some of our type 2 diabetic patients, their metabolomic profiles were very similar to some of the non-diabetics. And so what we'd like to do is we'd like to add another layer, another network, and ask the question, well, how are they different in their protein polymorphism? Or how are they different in gene expression? Or do they have a specific SNP? Or maybe some kind of epigenetic change or methylation on a gene. And using these extra layers, now we're going to build up kind of a new classification. So you are no longer diabetic and non-diabetic. You are actually different subsets of diabetic because you have differences among all of these layers. And so this, extrapolates to other very important pursuits like drug response and things like that. So you are unique, and your uniqueness is captured in this kind of hierarchy of this signal transduction cascade. Now, kind of the typical methods for integrating the various omic domains are typically some kind of a biochemical pathway analysis where we look at changes in metabolites and in genes or proteins simultaneously, so that's very helpful. Other methods are to essentially extend this idea of a metabolomic network and add genes and proteins, so we can connect our maybe coding gene to a protein, and then a protein which catalyzes some metabolic transformation to two metabolites. So now we've incorporated those together. Another powerful connection is this empirical correlation where we just look for metabolites levels which are increased with maybe protein abundance and also increased with gene expression, and we hope to kind of build some kind of a biological insight. In reality, probably a combination of all three of these techniques is probably going to be the optimal solution to how we can do omic data integration. Now, I'd like to spend the final couple of minutes just thinking about, how can some of these machine learning tools that we hear like out of metabolomics, how can they potentially be applied in the metabolomics area? So for example, computer vision. So I think many of you are familiar with how great Google is for classifying cats in YouTube videos or doing all sorts of image classification tasks. It has also a very powerful PageRank or website ranking algorithm where in seconds it can screen through billions of websites and find me the best one that I need to do my cat research. Or for example, deep learning, which kind of underlies everything, all of these various systems. Like how can deep learning be applied to metabolomics? So there have been some evidence of success of these methods applied to metabolomics, but really more what's happening is like omics in general is being kind of transferred into the system of where these methods were originally applied. So for example, there's still most of the success on doing some kind of image processing or some kind of methods where we can encode this data in a form that the methods are already being used in that form. And one thing that's not really talked about, we really need to consider is we really need to achieve a massive scale for metabolomic data to have these methods be applicable. So many of the algorithms like the image recognition, they're trained on billions of representations. And also the data is encoded in a very different manner. And so how can we in the metabolomics area, how can we achieve this scale of data? And I mean, naively, we might think, oh, well, let's make a repository. Everybody will submit their data, their experiments, and then this will be the kind of the corpus of training data that we're going to use. Now, I think that could potentially work, but we're going to need to capture so much metadata, understand all of the instrumental conditions, the experimental design. Studies are going to need to have quality controls, have very standardized for us to be able to do this. But in the future, we might be able to do this eventually. Now, there are some areas where there has been very unexpected success of biochemical deep learning. So here's an example of deep variant. So this is a system built by Google, and so what this system is trying to do is it's trying to identify SNPs, or single nucleotide polymorphisms, or indels, or gene deletions or additions. And this is actually a very difficult task. And what these guys ingeniously did is they took their genomic sequence, these base pairs, and they converted it to an image. They literally made a PNG out of the reads. And then they used this very powerful Inception, this machine vision library that was already trained for Google, and they retrained it to now predict SNPs and indels. And it actually performs very well. So this is very ingenious. But one issue is that this is really a black box algorithm, so you don't know how which things are more important or less important. You don't have any weights in the model. Most researchers are going to be prevented from doing kind of anything even close to similar, because there really is a high degree of difficulty of implementing these kind of deep learning methods that really will preclude most biologists from doing this. So you need to be very kind of specialized in this area to use this. But I think there is evidence that maybe eventually, if we reach the right scale, that some of these neural network methods can become these universal data encoders. And what they can do for us is essentially they can create new features, identify new relationships that were never part of our data, that these kind of emerge as part of this neural network system. And so, in summary, what I've gone over is that metabolomic analysis really is already kind of integration, a large deal of integration of analytical methods, biochemical domain knowledge, and experimental data. And that network analyses and mapping are actually a very powerful way to combine very orthogonal information like statistical and functional machine learning into a system where you have some kind of a biochemical or chemical context, and then you're easily able to visualize and experiment on it. And the combination of both machine learning and network analysis really can provide this flexible framework which can generalize to other omics and allow you to do all sorts of interesting data analysis and visualization tasks. And so with that, I would just like to thank all of you for your attention. If you're interested or you want to get more information about anything I talked about, please feel free to email me at createdatasol@gmail.com. Or if you want to read more about some of the tools I've been building, you can check out createdatasol.com.